Okay, so it's that time of the month again. I hope I'm coming in loud and clear.
You
Works for
are?
me. Cool. First things off, I would like to apologize for last month. There was an issue with the Zoom recording in where I started the meeting and it didn't create the recording, even though I got the Zoom voice notification that it started a recording. I don't know what happened there. So unfortunately, last month did not get a recording when I went to go find it, either on cloud or on my local machine. So I do apologize for that for those who wanted to catch it. Um, for this month, well, for those who I should rather start off by saying, for those who are joining us for the first time, welcome. This is the Tucson Amateur Astronomy's Fundamentals Group. We typically go over just general topics in astronomy, trying to keeping it at a high school to college level, cover uh, a large variety of topics over the years. We currently have one semi-recurring series called the Astronomer of the Month, where we highlight a notable astronomer, or rather, can be contemporary astronomer, which is the case of tonight with Pete presenting on Sara Seager, or more commonly, it's been a historical astronomer who has made contributions overall to astronomy and things typically keeping in the theme of astronomers who had an impact on things that we as amateurs can participate in or can make use of, if that makes sense. Has generally been the overall theme. We also typically have a main presentation, which covers a more arbitrary topic, which in the case of tonight is for me to give presenting on a selection of astronomy tools that were used before the invention of the telescope. And so tonight, we'll lead off with Pete and his presentation on Sara Seager. Take it away.
Okay, thank you, Connor. Let's see if we can get the right. There, that should work. Everyone should be able to see first page. I just got to move the
I'm
attendee slide bar.
I am still getting there it goes. Now it's through.
Now it's good? Okay.
Yes.
So, thank you. Good evening. Always a pleasure and always an honor to present before this group. I've done a number of these Astronomer of the Month presentations. This is a little bit different. This is the first time I'm presenting on an astronomer who is still with us. So it's kind of fun to do. In fact, one that was actually born after I was born. So even better yet. Um, Connor made mention, usually some notable astronomer that's had a significant contribution. I would submit that Dr. Sager is also a notable astronomer, and you'll see the reason for that as I go through my presentation. But anyhow, so we'll go ahead and start. One question I will ask, if someone could speak up, is anyone ever met Dr. Sager, been to one of her presentations? Because this is the first case where we may have someone who may have had prior contact with her. So if you know anything about her, and as usual during my presentation, don't hesitate to shout out if you have a question or a significant item of information to present. Okay, and there we go. As usual, I'll go a little bit over some of her personal life, education, work, legacy, and the references that I used for this particular presentation. Like I say, it's kind of nice to be able to present on someone that's still living, so I don't have the thing at the bottom with their date of death. But anyhow, Dr. Sara Seager was born in July of 1971 in Toronto, Ontario, Canada. Yes, she is a Canadian American. For the most part, since completing her bachelor's degree in Canada and doing a little bit of research. She's pretty much spent the latter portion of her life, probably since the early, I'm going to say 1990s approximately, in the United States, both going to school and also teaching. Her parents were David Seager, who later in life, probably about the time she either completed high school or when she first started college, I'm going to say in the late 80s, early 90s, became a world leader in hair transplantation. Before that, it was quite different. And her mother, and they split early in her life from the point where she was way before preteen. Sarah has a older brother, Jeremy, and a younger sister, and I can't remember. I think it was Melissa. Basically, they were fairly close in age, not widely separated, probably within 2 years of each other. Uh, and I mentioned the split between her parents because this created, an atmosphere that wasn't particularly nurturing, given the success and the notoriety that she was able to attain later. It was not an easy separation from their standpoint. They didn't have a lot. Uh, Her mother wasn't a real caring, nurturing person, and her stepfather was rather abusive when they did stay with them. I think the better part of her life is when they stayed with her father. They were still in Toronto. Her father lived on the outskirts of the city, and for the most part, her mother lived inside the city with her stepfather at the time. It's theorized for the most part about the only income that her mother actually had with the stepfather was from child support provided by her father. But if anything, her father probably provided a little bit more of a nurturing environment for some of her education later. Uh, Sarah, even from the standpoint of early education, elementary school, she was an avid reader. Probably one of the more seminal events, and a lot of this comes is both in the literature about her, based on some of the awards and some of her biographies with respect to her current position, but also in her autobiography, which I'll get to in a little bit later. But probably one of the more seminal moments with respect to astronomy. She was actually on a camping trip. There wasn't a whole lot. Basically, Sarah, her brother, and sister pretty much had to create their own environment, given the environment they had with the split family. And for the most part, they used to create their own games, do their own explorations. They didn't have a lot to do, so they had to create a lot. So, if anything, they were somewhat that. But one of the things that did happen was Sarah was on a camping trip with her brother and sister, and I think it was, basically a male babysitter. And don't get this wrong, no negative connotation there. And this was actually a good experience because it was one of the first times, and she mentions this in her autobiography. They were on the outskirts of Toronto, far enough out where the skies were fairly dark. I suspect it was a moonless night. But she remembers very distinctly getting up or being up sometime late at night, opening the flaps to the tent, and the wonder of the night sky was exposed. And it's probably one of her first events that she mentions, and probably one of the first events that probably ignited an interest in astronomy. Later on, she'll talk. She talks. In fact, she talks about this. The supernova of 1987, 1987A, that I believe was it in one of the Magellanic Clouds?
Yeah.
Yeah, okay. And as I understand it, it was visible without the use of a telescope. I don't know if it was visible with the unaided eye. And
Yes.
given the fact it was the Magellanic, how she would have seen that, and I'm not sure how she would have seen that because I don't think she would have seen it from Toronto.
No.
Yeah, I
No.
think it was far enough south. So at some point, and maybe it was just a matter of being a news item, but this was also another seminal event, I think, in her early years, and specifically, this was about the midpoint of high school for her. I think she was 16 at the time, and she was very interested in this event. I don't think she actually saw it physically, but read up a lot about it. I'll talk a little bit about her education, at least starting out with high school. At one point, I think it was the last 2 or 3 years of high school, really probably created the foundation for what she was able to accomplish later. But a little bit more about her personal life. Um, it goes without saying, if you know anything about Sara Seager, she, given her, early life prior to becoming an adult or even prior to her teenage years, it was a little bit rough at times. There was no physical abuse, but probably a lot of psychological abuse, particularly from her mother and stepfather. And no doubt her father probably tried to make up for a lot of this. But it's kind of interesting. As she went to college, one of the things that she got into a lot was hiking and canoeing, kayaking. Uh, I think basically she during her education, shortly after her undergraduate degree, she met and married Michael Weverick, who was very much, in fact, she met him more or less through this type of this avid sports undertaking with respect to hiking and kayaking. And they used to do quite a bit of this before eventually they were married and they had two sons. This was pretty much the majority of their pastime together. Unfortunately, he died in 2011, and I think at the time her sons were very young, preteen here. So, needless to say, this created a little bit of a burden uh, with respect to her life and what she was doing at this time. I think, of course, she was out of college, she was out of graduate work and was just starting to work. At this point, she's living in Concord, Massachusetts, because as you'll come to find out, she has spent the bulk and most of her life at the Massachusetts Institute of Technology. You know, a trauma that she went through. It was some years later, and I think basically the boys were probably getting into either teen or right about that changeover from preteen into teenage life, where she met a gentleman by the name of Charles Darrow. Interesting enough, she met him at he was an amateur astronomer, and she met him at an event uh, uh, that was sponsored by his organization. I'm trying to remember, I believe it was in Canada, but I can't say so specifically. It may very well have been somewhere in the New England states, but that's how they met and eventually did marry. And he ended up adopting her two sons by way of, basically setting the family up again. One thing I want to talk about too, and this was in her book, Widows of Concord. Uh, a few months after Sarah lost her first husband, Michael, uh, she made contact with this one woman and didn't know it at the time, but ultimately found out that this woman was also widowed, had suffered a loss of her husband too. And she became ingrained to a certain extent, became familiar. There was a group, and I call it the Widows of Concord. That's the way she makes reference to it. But basically, it was a small group of about a half a dozen, and I think it grew a little bit over time. Concord, Massachusetts at the time had a population of about 20,000. So it wasn't, even though it was close to the Boston area, it uh, wasn't necessarily a big city. So it was a nice town. But anyhow, there was a small group, and eventually uh, she joined this group somewhat as an ad hoc, but would attend functions, go to some of their gatherings, their parties, their talks. I think it assisted her in dealing with her grief over her husband. But needless to say, she was very direct. Didn't sugarcoat some of the things that she had to deal with. She had a lot of support. She was able to find support from some of these younger girls that she was able to hire to take care of her household. There were a couple that stayed with her for extended periods of time, so she didn't have to go through a lot of folks to help her out. Of course, she wasn't rich, was only able to pay them a modicum, but they stayed with her. But anyhow, she describes a lot of her social life vis-a-vis this Widows of Concord. She didn't have much of a social life, needless to say. Pretty much life was taken up by her kids and by work for the most part. But that, in a nutshell, sort of describes her social life, her basic life, leading up to the time when she started teaching at MIT. Backtracking a little bit, we go back to education. Jarvis Collegiate Institute was the private high school, basically, that Sarah attended pretty much, I would suspect, the last 2 years of her education prior to going on to university. Uh, Unsuspectingly to her and to her father, she did quite well to the point where she was the top student out of about 300 in this particular school with respect to science and math. She was also a musician too. I believe she played one of the woodwinds, but for the most part, yeah, the last 2 years she was in high school, she was the top student in pretty much most of the classwork. A little bit, I wouldn't say necessarily a surprise, but I think unsuspectingly to her because she just showed, she was, like I say, an avid reader. She wasn't real outgoing, but not that she was a bookworm. But I suspect, based on her autobiography and some of the other things I read and sourced about her, she was pretty much a no business, get down to work. And she was a very diligent student for the most part, is the best way I could probably describe that. And that pretty much carried over when she attended the University of Toronto and obtained her Bachelor's of Science in 1994 in physics astronomy. She spent two of the summers while she was going to college at the David Dunlap Observatory just outside Toronto, cataloging variable stars and managing some of the observing programs that the observatory had for the public. She was able to secure a Natural Sciences and Engineering Research Council of Canada undergraduate student research award. And ultimately, when she finished her bachelor's, she went on to Harvard and graduated in 1999 with a PhD in astronomy. The focus of her doctoral thesis was theoretical models of exoplanet atmospheres. Now, one thing of note with respect to exoplanets, it was pretty much becoming, anybody can certainly chime in here. I mean, as far as the discovery of exoplanets, a few had already been discovered up to this point, but it wasn't a sub-discipline within astronomy that a lot of astronomers were really working on. And for the most part, especially with respect to exoplanet atmospheres and being able to characterize those atmospheres, and you'll see later, of course, one of her main focuses of work was trying to identify signatures or precursors that might indicate some sort of life, not necessarily intelligent life, but some sort of life. Not that she was at that point here, but probably was getting close to it. But for the most part, and it wasn't that astronomers at this time were necessarily deterred, but there wasn't a lot of support for this sort of work. It was, I think, at this point, and Doug, I'll ask you to chime in, a little bit fringe about at the turn of the millennium.
That's the
Yes?
right word.
Yeah. You know, within about 5 or 10 years, it started moving out of there. And I would say more so, especially over the past decade and a half, it's really moved out of the fringe. And I mean, the science, it's not mature, but it has certainly matured quite a bit since then. And it just wasn't at that point. So it was somewhat of a risk. And it's not so much something she taught. Well, no, she does make mention of this, the fact that it was a little bit of a risk because there wasn't a whole lot of support for this type of work yet. So contributions of work. She was an MIT. She ultimately became an MIT professor. Her research has focused on extrasolar planets and atmospheres, specifically rare earth analogs. And what I mean by rare earth, not rare earth elements or rare earth metals, but the fact that earth analogs, as far as exoplanets, are very difficult to detect, to monitor, to identify. And so it's the rarity of this type or the size. And what I mean by Earth-like is primarily, probably up to about 2 or 3 Earth masses. And we look for some of those planets, Earth-like here again, that might be anywhere close to the habitable zone of its respective sun, which can vary widely depending on what sort of a star is the sun for that particular exoplanet. She's written a number of books, textbooks, Exoplanet Atmospheres, that was published by Princeton University Press, and also one that was published by the U of A Press, Exoplanets. Both of these came out in 2010, so almost 10 years after she obtained her PhD. Probably one of the things that really contributed to her overall financial well-being was a MacArthur Fellowship in 2013 for her theoretical work detecting chemical signatures of exoplanet atmospheres and developing cheap observatories to monitor planetary transits. And I'll get into that a little bit more too. But I think at that time, the MacArthur Fellowship came with about a $625,000 award. And it's pretty much no strings attached. People that are awarded with MacArthur Fellowship, the monetary portion of the award, they can pretty much use as they see fit. And it's not that she wasted it away on a lot of things, but it was a lot easier for her to be able to pay those that were helping her out with her sons and things of this nature, and being able to do, just some, basic recreation. No doubt it probably contributed a lot to some of the work she was also doing at the time too. Backtracking a little bit, she did her postdoc at the Princeton University Institute for Advanced Study. I think that, the Institute for Advanced Study, which was something that was created back shortly after World War II, at around that time, and Albert Einstein was certainly one of the first to be there. Many notable scientists came through there, but she was there for a couple of years. She was senior research staff at the Carnegie Institution of Washington through 2006, and then we arrive at 2007 when she joins the faculty at the Massachusetts Institute of Technology. Physics and planetary science, she obtained tenure within about a year after she first joined the faculty. She was a full professor within 4 years, and currently the class of 1941 professor chair, which is no doubt an endowed position, endowed probably by the class of 1941 at MIT. She is also the professor of planetary science, professor of physics, and professor of aeronautics and astronautics, which might seem to be a little bit out of her ballpark, but as we look into some of the projects we get in, that she got involved in, it's a lot more understandable that she was actually involved in that aspect of some of the projects that she was working on. She was elected a Legacy Fellow of the American Astronomical Society in 2020. That advances quite a bit because we're actually going to put in with a little more filler here too. A couple of the big projects she worked on, and one of the ones that she talked about quite a bit in her book, and something that she was very passionate about. She was chair, and backtrack a little bit too here with respect to, it's always been interesting and fascinating, some of these astronomers. No doubt, in fact, there have been a couple of astronomers I talked about. There was one from back in the previous century, and in fact, God, I wish I could remember her name. But as far as females breaking into the discipline or the arena of astronomy, it's been somewhat difficult. I mean, the glass ceilings, I think, were busted. I don't like to necessarily use that term. We're busted for the most part in the previous century, but yet, when Sara came into it, there was still a little bit of work to be done in that area. But I think it's gotten to the point, and this is truly the remarkable thing that I found out about her is, she earned some of these positions, and these were significant leadership positions in some of the projects that she worked with, both at MIT, with NASA, some of these joint collaborations. And coming back here, she was chair of NASA's Science and Technology Definition Team for Starshade. You can see the picture off to the right. And basically, what Starshade is having an occulting disk working with a space telescope. Now, in this drawing or in this rendering, they're fairly close, where in actuality or practicality, they wouldn't be. And I think the space telescope's turned the wrong way. But anyhow, the occulting disk would be some distance away from the telescope. And the whole idea is to basically occult the bright star and, leave it possible to expose these dim exoplanets so that they can be studied primarily through spectroscopy to determine what are the contents, what are some of the likely components of a given exoplanet's atmosphere, which here again was some of the main work that Sara was involved with. Additionally, she also, since 2020, she's worked on another project. I don't think this is launched yet, and if anybody knows differently, please let me know. But focused on Venus with the discovery of biosignature gas, phosphine, in the upper atmosphere. Here you can see a picture below. It shows two technicians working with the basic sensor or the satellite that would be dropped through the Venetian atmosphere. What you see off to the right is basically the big mylar bubble that would be expanded probably just prior to being dropped through the atmosphere. The little yellow container would be inside this, and basically it would, I guess, just float down to the surface. But primarily, it's meant as a detector to go through the atmosphere. One of the other things that Dr. Seager worked on was developing the Drake equation, for those of you who are familiar with it, with variations. The Drake equation pretty much focuses on what are the probabilities of intelligent life in our galaxy. And it looks at a number of factors: how many stars, how many of those stars have planets, how many of those planets are in the habitable zone, how many of those planets might have life, and it looks at intelligent life, the capability for technology. Whereas Dr. Sager's version focuses primarily, not necessarily on intelligent life, but the fact that any life might exist. So it changes some of those variables just to look at those very specific items, not necessarily intelligent life. She was deputy science director for the MIT-led NASA Explorer mission test. I think a lot of you might be familiar with this as far as the Transiting Exoplanet Survey satellite, where a lot of these exoplanets have been discovered, a lot of it through the transit method, where the the sensor, the telescope, will look at the change in the light luminosity. The luminosity of a star as an exoplanet passes in front. Of course, this only works for those planetary systems where a planet, looking at the aspect relative to Earth, where we'd be able to see such a transit, not necessarily looking from, say, above the planetary disk, but basically laterally through it, and then having the opportunity to see some of these planets actually go in front of their stars. But for the most part, early on, most of the detections, of course, were primarily, Jupiter, Saturn size, Neptune size, and a lot of them were hot. They were fairly close to their suns. A project that has since terminated, and she was Dr. Saber's principal investigator, was Asteria, the Arc-Second Space Telescope, enabling research in astrophysics. And these were basically, and you can see a picture over here, these were CubeSats, which are very small satellites, and there was basically a group of 6 of them. And this was to record photometry to locate exoplanets. This was a joint MIT and NASA JPL collaboration. It launched in 2017, was supposed to be operational for only the original mission parameters are only for 90 days, but they essentially operated for about 2.5 years. I don't think there was a whole lot of science going on at the end, but basically they were able to continue for some time. And then, of course, ultimately the satellites ended up coming back through the atmosphere as their orbits decayed. Bring this picture out again. This shows Dr. Sager with her 2 sons. This wasn't too long ago. This was taken there it is, August of 2023. They're quite well grown up at this point. But just to highlight, here again, she continued on, and a lot of her trips across the U.S. And overseas, deal with hiking, outdoor type activities. She continues to do that today. She's gotten her sons into it, and her husband is into it, I think, to a certain degree, but I think she's primarily in it. But this was a picture that was taken. You're going to see some of the legacy items, the Kavli Prize. And, Doug, you know much about the Kavli?
Beg your pardon?
Do you know much about the Kavli Prize? Because
I know
I understand
nothing.
it's a big deal in astrophysics.
I know nothing about it.
Oh, okay. But this is supposedly a big deal. And she got this just last year. But this was actually a picture from her biography that appeared in the Kavli Prize. But I thought it was kind of a neat picture to show because, like I say, all throughout her life, with her family, this has been one of the focuses going outdoor activities. And certainly, I think, given her, helped sustain her in her work, because I think some of the work that she's done has been rather remarkable for anybody. Some of the legacy items: Sackler Prize for analysis of atmospheres, internal compositions of exoplanets back in 2012. She's been appointed a fellow of the American Association for the Advancement of Science. Numerous prizes, book prizes, and work prizes. She's well recognized. She has been out there quite a bit in the public eye, particularly in the previous decade, promoting the type of work she does, particularly with exoplanets, trying to characterize their atmospheres and trying to identify signs of life potentially, or at least some of those precursors that might need to be there. This is a science that's still developing. There's still quite a bit to go here, particularly with respect to trying to positions, and I say sensors, not meaning just telescopes, but any sort of sensor or detector that's able to identify some of these components that may, indicate the potential for life. And here again, there's still debate on, what some of those, not necessarily elements, but some of these chemical compounds that are essential. That's a debate that's still going on, especially with respect to those that are specializing in exobiology. Exactly what needs to be present for life to be present on a extrasolar planet, and so that debate's still going on. Continuing on, elected to the Royal Astronomy Society of Canada, various other organizations. And in the middle here, you'll see the Los Angeles Times Prize for Science and Technology. This was the book that I read. This book a couple of months ago. It was a very fascinating read. It isn't real long, but I would urge you to, if you've got some time. I think I downloaded had both the Kindle and the Libby version. but I think I read most of this book. It was a very good read. I really enjoyed it. It's a fascinating story. I would urge any of you to take a look at this, but pretty much it covers, Dr. Sager's life from when she started basically in elementary school and leads up to pretty much the present. The book came out, I believe. I have to take a look at my, yeah, 2020. Okay, so 5 years ago. But there have been some other, the Kavli Prize last year, Asteroid 9729 is named for her. But that's basically in a nutshell. These are the references that I used. And thank you for your attention. Are there any questions or comments? None. Is everybody still there? Connor, are you still there? Uh-oh.
I could hear you, Pete.
Oh, okay. Thank you, Bernie. Okay, I'm just if there's no
we-
questions, I'm going to go ahead and stop the share and Connor can set up for the next one.
I just made it online, so could you go all over it again?
What's that? I tell you what. Check the recording out next week, Bernie.
Okay, okay, that'll do.
Yeah,
Thanks.
I know. It was kind of, I actually ran through it kind of fast. I don't know what.
My apologies. I got my neighbor wanted to chat over the fence.
Okay.
Am I still there? It goes. Now my mic's working. I don't know what happened.
Thanks, Ross.
Thanks, Pete. Thanks again.
You're welcome.
And with that, we're just going to go jump straight into this next one. So, as I briefly shared at the beginning of this, I wanted, we've often talked about, equipment and things that we as amateur astronomers will, use or shop for or use for various side projects when we, take on, challenges such as those in the astronomical league's long list of observing programs. But we hadn't really talked about anything that came before the telescope before. We've at least, not directly, occasionally in passing when we've talked about various other historical astronomers like Tycho Brahe, but nothing about the individual devices that they would have used to make some of their discoveries and observations in any detail. So I wanted to see what we could pull up here and add to that. The criteria for this was simply that the tool had to have been invented and used before the invention of the telescope, which for those who are hoping to learn more about the sextant, you won't find that here because the sextant was invented in 1726, well after the invention of the telescope. While researching this, I didn't really come across too many devices that I could find, at least meaningful things to present on from a background perspective. But ultimately, the devices that I did find broke themselves down into three different categories. Devices that were used as clocks or some measure of keeping time, whether it be keeping the time of day or the time of year. Devices that were used as sort of rudimentary primitive star maps, and other devices that were used to help measure angles, which also made them more useful not only in astronomy, but in other activities such as land surveying. The first device that we'll talk about was if I can pronounce it correctly, was known as the Parapagema. And it was possibly invented in the 5th century Athens by two inventors named Meton and Euctemon. And this basically took the form of a rudimentary stick calendar with a central radial dial and slabs and holes for marking different aspects of the day and the year. There's a picture on the next slide, which I'll dive more into. And the basic operation of this is that you would just insert a stick in a specific piece on this stone slab to mark various aspects of the time of day, the time of year, and so forth. This is one example that was excavated. This is a Roman example specifically due to the Roman numerals on it. And it was actually excavated out of a wealthy Roman's house in Pompeii. We can see at the top there are basic femiciles of individual Roman gods. These are actually representing the individual days of the week, with the leftmost date being Saturday. They for some reason decided to start their day of the week on the day that we end on, and rather than on Sunday. And so when they would to mark the day of the week, they would simply just take this little stick peg, and move it down to each individual respective day. Off to the side, we have pegs for the 30 from 1 through 15, and then 16 through 30 to denote the individual day of the specific calendar. And then the center here is was primarily used as a form of the marking of the month. So although this does look like a radial dial, there are actually 24 pegs to denote the month, and the month would land on the solid lines here. Each of these individual faces represents a piece of the zodiac, and I should just turn on my laser. Represents a piece of the zodiac, which would where the sun would be during that particular day of the year. So eventually, serving as a way to mark the individual months. So I believe, can't quite think this is Cancer over here. If that looks like a crab, it's hard to make out some of these individual markings.
There's Scorpion.
Kelsey, you're unmuted. Can you please mute yourself, please? I can. There we go. From there, we will jump over again to our good friends, the Greeks. There's actually many of the devices I were able to find did come from Greeks, although I did try to see if there were some earlier ones. Didn't get too much into that. But this is what's known as an anaphoric clock, is a primitive water clock, which was invented sometime in the 3rd century, again, by Athenian Greeks. And it was based on a 24-hour, based on a 24-hour system, much like ours. They did represent the individual days as 24 hours. And the disc on each arm, we can see represented the various constellations that you would move through. I wasn't able to quite figure out too much on how you actually were supposed to read this particular clock, but ultimately, with the water clock itself, you were keeping consistent water pressure, and it would just slowly turn on its face. And it's not quite clear to me what the actual blue sphere that the clock was on was, if it was just or if that's a metal sheet. It's kind of hard to see from the lighting and rendering here if that's just a hanging metal sheet or an actual sphere that the clock itself is mounted on. Looks like it's a metal plate. It's an off-centered metal disc that's just behind the individual arms. So representing a sort of, this would be your region of sky during the day and during the night with this, but like a simplified planisphere to a certain extent. Now that I look more at this image. And perhaps one of the oldest devices used for timekeeping comes in the form of the sundial. And specifically, this is the gnome, which is the part of the sundial that casts the shadow when you're using it to tell time. This is the earliest form of a sundial that we currently know about, where it's lacking. It's basically just a giant stick in the ground or an obelisk in some cases. And the earliest known gammon that we have found dates to about 2300 BC China. In addition to being able to tell time, these were also used to help track solstices and equinoxes. This follows from the same principle. For those who have tried to photograph the precession of the sun through the sky at the same time of day to capture an analemma, this is the same principle, just much more primitive form where you would just look at the shadow at specific times of the year to determine if you were in a solstice or equinox period. And this primarily served as a way for farmers and religious activities to time their activity, religious festivals to time their activities in Chinese culture, and eventually in others as well. It's just a way to, hey, we need to know when to plant things. This is a more semi-modern example of a gaman. This is specifically a replica from a Chinese compass and gnome combination made in sometime in the 1400, 1000 to 1400 AD. You can see the compass here, the compass needle over here on the left, and the gaman is actually the stick figure here, and the rest of the sundial itself is comprised of the markings seen around the disk face. And the gamans would actually be elevated to a rough representation of your current latitude, which is why this is on a sort of pop out disk here, because you would have to elevate them to your latitude, or rough telling of your latitude. We then move on to the amylary sphere. I'm pretty sure many of you will recognize this in the next picture of knowing exactly what this is. But this device was actually independently invented by both the Chinese and the Greeks in the 3rd and 4th century BC. This takes the form of a rather complicated looking globe, and it used a series of circular arms in order to annotate various astronomical features. With modern amylary spheres, when you do see them containing various features that I'll point out here in the next picture. And I also have a video after that to kind of go over how you would actually use and manipulate an amylary sphere, because I didn't want to write out 7 slides on how to actually use these things. So this will be the first time I've tried to do a video on these. I don't know if the audio will come through. May have to play with it. If it doesn't come in quick, I'll just move on and skip the videos. But these spheres were used to denote various key features on that played into making primitive measurements, such as the ecliptic circle, and the individual constellations of the zodiac, in which is the constellations that the sun will move through as it moves across the sky during the course of the year. What an arm representing called the celestial cooler, which is a north-south, which is basically a north-south meridian that passes through Cancer and Capricorn zodiacs, which is used to track the timing of the solstices. The equinoctial cooler, which is a north-south line that passes through the constellations Aries and Libra on the zodiac circle for tracking equinoxes. There will be additional arms potentially for denoting the positions of the tropics of Cancer and Capricorn, and then later models would add the circles for the Arctic and Antarctic circles. So this showing the amylary sphere and all the individual pieces. The flat disk here marking the horizon, and then lines calling out each of the individuals. You see this little thin band up here near the top representing the Arctic Circle. We have the thickest band here for the ecliptic plane and the zodiac. We have 2 smaller bands here at the top and here that's kind of masked by the horizon that would represent the 2 tropics, the Tropic of Cancer and the Tropic of Capricorn. We have the band marking the equator, and then another band down here at the bottom marking the Antarctic Circle. And we see these 2 north-south bands here for the 2 cooler circles for the solstice and equinox tracking. And we'll see if this will play. Let me switch back to mouse. 1 second. There we go. Mouse. Do you guys have audio? Are you guys catching the audio from this?
No.
Let me see.
No audio yet.
Let me advanced sharing options. There's an option in Zoom to share audio. I'm not sure where that
You try the advanced sharing off the share
share
button.
computer sound, stereo
Um,
fidelity. We'll try this.
If you're like me,
There you go.
you've seen objects like this for years and wondered what they were and how they worked. They tend to show up in museums or libraries or
Are you able to hear someone
paintings.
speaking?
Yes.
Okay, cool.
To the parts of it. The armillary sphere consists of a base with a horizon on it, meant to indicate the visible horizon, or what could be seen in the sky from the position on Earth where this is set to. Inside of the horizon rests the device. It's made up, this big ring inside of it is called the meridian, and it represents the midpoint of the sky if you were standing in the northern hemisphere looking south, or in the southern hemisphere looking due north. Rotating inside of the meridian are a bunch of other rings. This largest one here, the most prominent, is called the ecliptic ring. It has Roman numerals on it indicating the various months and dashes indicating the various days. It is tilted relative to the other rings, and we'll run over what that means in a little bit here. The other rings you see here prominently, this top one here is called the Arctic ring. The next one down is the Tropic of Cancer. The next one down is the Equatorial ring, then the Tropic of Capricorn, and at the very bottom is the Antarctic ring. These vertical rings are called couleurs, and the one that runs through the 6 and the 12, indicating the summer solstice and the winter solstice, is called the solstitial couleur. And the one that runs through the 3 and the 9 is called the equinoctial couleur. Now, if you want to use this to calculate celestial events, you need to first figure out where on the Earth you want to calculate for. You can see our little representation of the Earth inside there. It's mostly there just for amusement, I guess. As far as I'm concerned, it's not accurate enough to do any measuring off of. But my particular location is about 45 degrees latitude. So starting here at the equator, I count off this direction, 45 degrees. These are little marks are 5 degrees apart. So 10, 20, 30, 45. 45 degrees. And I'm going to set this right so that it is on the horizon. Like so. Not quite locked in. There we go. So this is meant to represent the tilt of the Earth for me at 45 degrees latitude. Now, I find today's date. This is the 10th month, roughly a third of the way through it. And I'm going to put a little sticker on there so we can find that again. Now what happens is that as I rotate this, you can see how the sticker traces an arc up and down from the horizon to the meridian down to the horizon. This is actually representing the path the sun will take in the sky for me today. And if I have this thing calibrated right, I'll be able to measure in degree marks here on the horizon where I would expect to see that sun start, and then rotate it up to the meridian and see how high it would go in the sky for me today. And then rotate over here and see where on the horizon it would set. I've done some calculations, I've done some test runs with it, and it's fairly accurate. What I don't think I have perfectly right are the spacing of the days here. But it's interesting to see that if I change from October, where the path of the sun is fairly shallow to a date like the middle of summer, or sorry, the start of summer at the summer solstice. You can see the path is much, much steeper, and that it goes from beyond 90 degrees up from south up to about 60 degrees. What is that called? Declension or elevation. You can do the same thing just by rotating this for different places on the Earth. So interestingly, let's go to the North Pole. Now we are set to the North Pole, and you can see that here on the summer solstice, that sun's going to go rotating around the sky, and it's never going to actually go under the horizon. But even for a date like today, if I go back and set this to October, to a third of the way through the October, and I set this back to the North Pole position, that already at the North Pole itself, the sun is never rising above the horizon. If I go to the equator, like so, then you can see that the sun traces a path almost directly overhead. And on the autumnal and vernal equinoxes, the sun traces a path directly overhead. And then on the summer and winter solstices, it's actually 23 degrees north or 23 degrees south. So the day's a little bit shorter on those days than it is on the equinoxes, curiously. So in addition to telling you how high in the sky the sun's going to get, or other celestial bodies, and telling you where it's going to rise and set, you can also use an armillary sphere to calculate what time an object is going to rise and set, at least relative to local solar noon. Now, a higher quality, a higher definition armillary sphere would have degree gradations on each one of these horizontal bands, so that I could see that, let's see, we here are in the summer solstice at this particular latitude. I can see how many degrees it is from there on the equator over to sunset, and that degree, let's say in this case it is, I don't know, 70 degrees, and if I divide 70 by 360, I get the percent that makes up of the entire rotation of the Earth in one day, and I multiply that percent times 24 hours, then I would learn how many hours before noon the sun is going to set. And the way it works out is that's the same number of hours after noon. Sorry, hours before noon the sun is going to rise, and then how many hours after noon the sun's going to set. So with a simple device like this, if used properly and if tuned well, I can tell the time of sunrise and sunset for any place on Earth, for any day of the year, which I find pretty amazing. There are other more complex things that can be added to an armillary sphere. Sometimes they have a...
I'm going to go ahead and end that video there. Any questions or comments on that? There's kind of a lot to go through with that. Although now you can probably impress your friends the next time any of you show up to museums like, I don't know how to actually use one of these now, rather than just looking at it and spinning it around really fast to see how quickly it goes. All right, 1 second here. Just checking sure I didn't miss anything in the chat. And then our last, next slide, please. Come on. There we go. Okay. Sorry about that. Am I still audible? Making sure my mic didn't cut out during that video.
Yeah, you're fine.
Okay, thank you. Our next device is the astrolabe. This is essentially one of the first, well, was originally conceptualized by allegedly by Ptolemy as a miniaturized version of the armillary sphere, although it wasn't invented until sometime after he sort of by the Greeks, sometimes after when he first had this thought. It takes the form. The astrolabe is essentially the precursor to what we use today as the planisphere during our own observations for, just seeing what constellations are up in the night sky. They operate on similar principles, taking the three-dimensional spherical sky and then flattening it down into a two-dimensional circle. And like all planispheres, these are each astrolabe was built to a specific latitude range, although later versions included a metal faceplate which you could swap out to different locations, as you'll see also in a video that I found that was made by the British Museum. These acted as very primitive pocket computers. Although most of the instructions I found on how to use an astrolabe for today denoted about how to use it basically to tell the current time in various ways. By the 10th century, Arab astronomers who had absorbed much of the Greek learning and knowledge had documented well over 1,000 uses for the astrolabe in a book that was more than 380 chapters, which is a lot to document, which is surprising that you could divine that many things and spend over, that much, use that much precious paper to document the uses of an astrolabe. So it shows just how important of a device it was to Arab learning and Arab knowledge itself, that they just felt that they had to go through and document so much about this device. This is the reverse side of an astrolabe. It's showing individual clock periods as well as constellations, and in some cases star charts. This back piece here, which will be shown in the videos I have coming up as well, was used to help sight the sun as a primitive reflection finder scope, not reflection, shadow finder scope, like we see, like the kind you would use today if you were trying to sight your telescope on the sun for solar observing, where the sun would simply just shine through one side here and then cast a shadow here on this back side piece. So casting a shadow from this here on the right over here onto the left-hand side. Sort of a primitive pinhole projector. And then you would use that on the front face to help tell you various things about the night sky or, star positions as well. Try. So this is the last video, and I think I have one more device to talk about after this, and that will wrap this up.
When it comes to AI,
YouTube ads.
there's something big happening. The smallest things are creating.
Hi, my name's William Greenwood. I'm the Al-Bukhari Foundation Curator of the Islamic World at the British Museum, and welcome to my corner. So, part of my job is working on the new Al-Bukhari Foundation Galleries of the Islamic World, which will be opening in 2018. And one of the displays, or redisplays, in fact, will be of our collection of Islamic scientific instruments, particularly those involved with reading the skies, so things to do with astronomy and things to do with astrology. The best description, or the best explanation for astronomy and astrology, the difference therein, is that astronomy is telescopes and astrology is horoscopes. So astronomy is actually looking at the skies, trying to understand celestial phenomena, stars, planets, so on and so forth. Astrology is what those stars and planets and phenomena are supposed to do to us on Earth. Today, astrology is seen as somewhat less scientific. It's something that you see at the back of a newspaper generally. But for the very, very, very longest time, from very earliest times up until really very recently, astrology was seen as much of, maybe even more of a science than astronomy. Astronomy was there to serve astrology rather than the other way around. There are a number of different objects that you can use to find out about the sky, and the most important one, and the most long-lived one perhaps is the astrolabe. So if you imagine it, this is the universe in the palm of your hand, or at least the universe that you can see and comprehend. This is you right here. This is the horizon. This is directly above you, and this is out of sight because it's below the horizon. Each of these pointers is for a particular star. And so with this, you have a whole map of the heavens right in the palm of your hand. It's used for all kinds of things, or it was used for all kinds of things before the invention of workable clocks. In the 10th century, one astronomer worked out that there were about 1,000 applications for one of these, ranging from the religious, so you can find the prayer times, or indeed the direction of Mecca, which is incumbent on Muslims. For prayer, you could tell the times for example, crops to be planted, for taxes to be raised, rising and falling of tides, all kinds of things. So this is your basic instrument, as it were. Let me go through this very, very slowly. How does this work? Well, I think the first thing to do is to explain all the different parts of it, because each of them has a very important aspect to it. So, to begin with, this is the ring, this is the halqa, which is connected to the kursi, which in European terms is called throne in English. So, why is there a ring on top? Well, this is to hang it from, so that you have it even, and you can hang it at eye level, so it's always flat. So this is always at eye level. It shouldn't be swinging about. If you hold it in your hand, you're not necessarily holding it flat. This bit around the edge, this is the this is the mother, or the mater in Latin, and this holds everything together, and it has information, so it has the zodiac on the outside, it has zodiacs, it has times, it has days, it has all kinds of information. Inside, there are plates, and they're held inside the mother. So you can have sometimes up to about 5. They're often engraved on both sides. So depending on how far north or south you are, you'd use a different plate. So you'd have maybe one for Mecca, you'd have maybe one for Cairo, you'd have maybe one for Cordoba. And you can change them. On the front here, this bit with the star pointers, this is known in Latin as the reti, which is the net, but in Arabic it's the ankabut, which means the spider. And this is your map of the stars. Each one of these points to a different star. And all of this is held in suspension by this. This is the pin, the faras. And then finally, on the back, you have the alidada. So this is the ruler. This is what you use to sight with. Now, you have to be quite the expert to know how it works exactly, but I can give you a generally good idea. So, what you want to do first, if you want to tell the time, is you need to use this. This is the alidada. You have to imagine that this is hanging straight. I won't hold it too much like that. And you would line this up with the sun. As such. Imagine the sun is over there somewhere. Obviously, you wouldn't look through it to sight the sun because you'd go blind. Everyone knows that's a bad idea. But you put your palm there and you'd make sure that the sun was shining directly through it. And then this would point you to a particular date, a particular time. You'd actually use the zodiac to tell you what day or time it is. And then you would use the front and you would bring it to the same as that, and it'll tell you all kinds of things. It'll tell you where stars are at that time. It'll tell you what you should be seeing in the sky. You can also do it in reverse. You can use a star if you know where it is on the pointer, and then you can line the alidada up with that, and it will tell you the same information but backwards. So that's a very, very rough idea of how it works. I hope that makes some kind of sense. Does it make sense?
Again, I hope that at least gave a rough idea. Like I said, I couldn't find much more on the ways that people just used it predominantly to tell time, even though there are over 1,000 documented uses from it. And I didn't want to spend far too much time on this presentation just going into a device that had that many potential applications. The next device is a good one that's we've seen before in some other meetings, known as the quadrant, which was created by Ptolemy, or credited as being created by Ptolemy as an improvement over the astrolabe, but it believes, but something artifacts make us think that it predates him by quite a bit. Although I couldn't find exactly what artifacts or they were referring to during this period, but my guess would probably be something out of Babylon. The first no, gotta get ahead of myself here. There are some samples of a quadrant that was used potentially by civilizations out of the Indus River area in India between 1500 and 1000 BC that they used to measure solar eclipses, although I wasn't able to find exactly how they were doing this. And the quadrant essentially is just half of a protractor. It's just the one side of a protractor measuring out 90 degrees. And these would be built to many different scales to give you more precision or less precision depending on your particular use case. Many of these would often fit in the hands as a sort of portable protractor. Others would be known as mural as in picture quadrants, and would take up entire rooms. These devices would, in order to operate them, that's just, like I said, half of a protractor, and it has a weighted line on it. And you would use the weight, you would sight through it with your eyes, and then mark off with the weighted line where the angle terminated with respect to the ground level for you. As I said, we've seen these before in other meetings. This was actually used by many astronomers. Notably, here is depicted here is Tycho Brahe at his observatory and how he would use the quadrant to make his observations. So we see here just the sheer scale of it to give more precision in determining various angular markings. And if my interpretation, looking at this picture, is correct, there are hangings here on the side for marking the angles as they are pointed out or called by Tycho here and his assistants, who would then record those observations. Although it's not quite clear exactly what they would use to, if he's just pointing here in this mural for the sake of artistry, or how they represented, or if this gentleman back here, is the one who's actually marking the angle, and Tycho is simply just saying, "Go here, looking at this, go the object here that I'm pointing out," and this assistant back here would then mark that angle. Again, very simple devices and their operation, which made them also very useful for many other applications outside of astronomy, specifically within surveying for land, and also for navigation as well. And then the next device, and I'm thinking this is the last, is again another Greek instrument known as the dioptra, which was also a device used to measure angles. It was notably used by two names that we might be familiar with from Greek mathematics, Euclid and Geminus. And it was used to measure angles within respect to the horizon as the reference point. So this is just, we would say that this is a semi-primitive or a more complicated form of a compass, but without being able to always point you to the north, due north. It consisted of a long tube, which we can see here, which was used as your sighting. So this would be the sighting crosshair that you might look through, or it's the other way around and just can't see it because it's blocked by the Zoom panel for me. And you would then use that, and then you would then measure with this the gear ducts down here is actually a protractor, and you would use that to measure angles, vertical angles up or down within respect to the horizon. Any questions, comments? I mean,
Comment.
Yes, Doug.
I'm a nerd on history stuff. I actually used to own an armory sphere, a quadrant, and what was the other one you did? Oh,
The
the
astrolabe.
astrolabe. I had all three of those at one time. Right now, the only one I've got is the sextant. Um, the Astronomical League has two programs related to this. They have a program that's literally called, let me pull it up. What's it called?
Astronomy before the telescope.
Thank you. Astronomy Before the Telescope. And then, of course, they have the Analema program. And the Astronomy Before the Telescope, you build some of these things.
But yeah, notably, the video that I shared for the armillary sphere that was shown in that case was actually 3D printed by the video maker. He just called that out in a portion of the video that I skipped over because it was a little bit of a diatribe. So I hope you actually learned something. Next time you might show up in a museum with some friends, you go, I know how to kind of work one of these. That's kind of the idea going around here. We see a lot of these from time to time in, when we start trudging through astronomy forums or the historical or learning more about the background and history of astronomy. So you go through that, and it's always like, how do we use these? Yeah, now we know a little bit more about them.
Thanks for the video on the astrolabe. I have a brass one, and I'll be darned if I can find it. I'm gonna have to search the house top to bottom and see if I can find it again. I need to bring that out of the closet.
Yeah, they're definitely one of those. You look at those, you're just like, how do I use this? Looks like a really funky globe. And I was always like, how do I? So it was really cool to doing the research on this is learning exactly how to actually use and read one of these devices. So definitely one of those other skills I thought I'd never ever have to learn or have reason to use.
That's what computers are for, Connor.
Hey, if an EMP comes and wipes out all the computers, good luck. There is one other device that I didn't put on here intentionally, which others might have picked up on, and it is the Antikythera mechanism. Mostly because that device itself hasn't been fully fleshed out exactly how it was intended to be used. It's mostly theoretical because we don't have any other reference points about like exactly how we know it was a device to measure time and other astronomical devices, but without a full reconstruction of the actual mechanism, it's kind of still more theoretical. And I wanted to ground it on these are things that we know how they were used, and I couldn't justify that with the Antikythera mechanism, so I left that out of this presentation intentionally. Although it is itself a very complicated device, and it is also credited as being the first known primitive computer. So with that, that's going to wrap up my talk, and I don't have anything else. For next month, I was wanting to ask for those who are thinking they do want to come for next month's meeting, is I wanted to try something a little bit different. We often, as people who just like to follow the news, will come across articles talking about latest astronomy discoveries. Sometimes you'll find things in Sky and Telescope magazine, for example, or Astronomy magazine. But I wanted to say, if we wanted to have a slot to share, hey, here's these cool things that I read about that professional astronomers or maybe even amateur astronomers have contributed or discovered here in current events. Like, for example, there was a research paper that came out here recently talking about how the cosmology problem of which came first, stars or black holes, and the evolution of the universe, and adding additional pieces of evidence to that line of trying to answer that problem, and how they actually, and the evidence they had for it when it comes around to finding the biggest known supermassive black hole that we've discovered to date. which is something I'll probably talk about. I hope to talk about next time. If I just didn't know if there are others who might want to contribute articles for that, or if they think that that's a good idea as something they might want to bring into next month.
I like that idea.
Hey, Connor, I had sent an email. I think I sent it to Pete when Pete was running this meeting for 1 month, a couple of months ago, about I would give a short talk about the new space weather Astro League observing program.
Oh yeah.
Oh, you did send me
I
that. I did
yes,
get you. You did say that.
I was under the impression I was going to do that tonight, but obviously not.
I
Uh,
had forgotten completely. I
okay,
apologize. That
so
was my fault.
you want me to do it in September?
Uh, we certainly can. I will add you that.
It's only going to be like 5 or 10 minutes, just a short spiel, so we can
If
still do
you
two other things if you want
if
too.
you have it now, you can do it now, or you can
Uh,
save it for September. I'll leave it
I
to you.
thought actually September might be better because I can actually show some data.
Okay, then I'll add you. I'll make sure to put you on my spreadsheet for September as
Okay,
well, so I do not forget this time. I
because
apologize, Doug.
I've been running mine now for 2 months, and so I'm getting some data. So um, okay. Um, Connor, something to think about now. We haven't done the constellations in a long time now. Um, and I don't know whether we've got new people attending the meeting that may not have been around when we did all the constellations. Uh, should we consider revisiting them?
I will. It
Okay,
depends on if
just a thought.
no, it's a good thing. It's a good question to ask. It's if those that I do that I would probably say we would focus on would be ones that we don't have a recording or presentation archived for.
Oh,
Because
some of the early ones.
because
Okay,
we have about 40 of them that are available on the YouTube channel. And if if I can direct people who want to go learn those to go to the YouTube channel to see those, then I that would be my preference.
okay,
But
understood.
I have a spreadsheet that has all the ones like that we do have YouTube recordings on as well, so I do have track of it. But it would preferably ones that I don't even have an archive presentation for as
Okay,
well.
that
So
makes
that
sense.
um, would be my preference on which ones we would do next. But
Okay, sounds good.
so with that, then I got some things for next month. I hope everyone came out and learned something, which is always good. And I will see everyone back in September.
Thank
Okay,
you. Good night.
good night.